Okay, imagine there's systems of PDEs there. So we're going to be looking at chapter 7, which begins at page 105 in your notes. So essentially, all what we've been doing so far, okay, so we've actually done quite a bit of work so far this term. It's gone quite a fast pace. We've looked at finite difference approximations, and they're all derived from the Taylor series. We looked at elliptic, parabolic, and hyperbolic equations, and we've looked at solving those or finding approximations of their solutions using finite differences. But up until now, all the equations we've solved are just single equations. We just have one equation, whether it's Laplace or whether it's the advection equation or the heat diffusion equation. It's just been a single equation to solve. What we're going to be moving on to now, and this is also what your coursework will be on, is solving a system of PDEs. Okay, so we're no longer going to be solving a single PDE, we're solving lots of PDEs which are in a system. Now, the reason why we want to be able to solve systems of PDEs is because real world phenomena, the physical world, things interact with each other. Okay, so if you have one thing that changes, it will affect something else. And often you want to model that. So take, for example, a fluid. Okay, so when we've got a fluid, it's quite a common application is what we do in the division, is what our research is on, is modeling fluid. Now, if we look at fluid flow, we have a number of different variables. Okay, so fluid, first one's density, which is given by rho. By the way, these variables do not form part of the assessment for this unit. So don't worry yourself about having to memorize all of these. It's just an example. Okay, so density. So if you're modeling a fluid, you have one variable, which is density, which is given by the Greek character rho, which looks kind of like a P. And that's a bit annoying in a minute. So I'll explain why that's annoying. But density is essentially the mass. So how much mass of fluid have you got? Okay, you've also got a velocity. How is the fluid moving? In what direction is it moving? And by what speed is your fluid moving in? You've also got pressure, which is the reason why rho is annoying is rho looks a lot like P. So when you're writing it down, it's quite common to make that mistake. Pressure, so force, ratio of force to area. Okay, that you have energy. How much energy is in your fluid? Temperature. What is the temperature of your fluid? Now, a change in any one of those will affect all the others. So, for example, if pressure increases, the temperature will increase by physical laws. If the temperature increases, the velocity may increase. If the velocity increases, your energy increases. If energy increases, your density may increase. And because the density is increased, the pressure's changed. Okay, so these are all interacting with each other. So it's all very well and good solving a single PDE, but often when we want to model sort of complex physical behavior, we need a system of PDEs. And we form these systems. What we do is we say, okay, let's have a look at what we're trying to model. And with all mathematical modeling, we start by simplifying what we're trying to model, and then we go from there. You won't be asked to form these PDEs, they'll be given to you, and that's what normally happens in practice. Okay, the PDEs which we'll be solving, called the shallow water equations, they were derived 150 years ago. Okay. We won't be going over that derivation again. What we'll be looking at is solving these equations. And essentially, if we look at fluid flow, which is what I'm going to base this lecture on, we have three sort of assumptions we're going to make, or three laws which we're going to apply. One is conservation of mass. So this means over our domain, the amount of fluid in our domain is going to be constant. So look, imagine you've got a fish tank filled with water. If you sort of tip up the fish tank, okay, some water will flow to one end of the fish tank, but the other end will decrease. Okay, so you don't create any extra water. The water just slosh around and move around. Also, conservation of momentum. So momentum is velocity times mass. Okay, so as water moves around, you can't add any extra energy into our system. And that brings us to conservation of energy. The total energy in your system is constant. Now, these are all the underlying assumptions to models of fluid flow. And they can be also applied to other things like gas dynamics, aerodynamics, etc. Saying all that, we do often add or take away mass, momentum, things like that, to model something, to influence a behavior. Let's say we want to model some sort of water waves. What we tend to do is we affect, or we add some energy in, or add some motion in to actually create some waves. So what we're not doing is we're changing conservation of momentum of energy, but because we want to model it. Okay, we don't have to really look at any additional techniques to solving a system of equations over a single equation. These are generally the same techniques. We may have to take into consideration some additional parts, but I'll mention that. Up until now, we've been dealing with a single quantity u. That u has been our solution. That u is a function and has some value, so your nodes have a value of u, and that's been the solution. Now u is a vector. So we haven't got a single value, we've got a vector of values. Okay, so our solution is now a vector. And the properties of the solution techniques for single PDEs also apply to multiple or systems of PDEs. So, for example, stability. We dealt with stability over the last couple of weeks. If something's not stable, it's not going to be stable for a system if it's not stable for a single PDE. Right, I'm only going to be discussing or using what we call the shallow water equations as a system. Now, there are lots and lots of systems of PDEs out there. This is just one example. Okay, it's how we solve the shallow water equations is similar to how we solve, for example, the Euler equations, which are a model of gas dynamics, which are similar to how we solve the Navier-Stokes equations, which is another model of fluids. Okay, so I'm just using these as an example. Also, your assignment is on the solving of the shallow water equations. I'll talk about your assignment after the lecture. Okay, so I'll lecture for about an hour and then we'll discuss the assignment. Okay, shallow water equations, often abbreviated to SWE, are a simplified form of a more complicated equation set called the Navier-Stokes equations. And essentially, these are derived by assuming that velocity in water in the vertical direction is negligible. So that means water doesn't flow up or down. Okay, that is a false assumption. If you think about water, okay, water sloshes all over the place. They're going to have some positive velocity in there. So what we've done here, what a guy called Sant Benant did, is assuming the velocity in the vertical direction is negligible, i.e. very small, we can simplify this equation set, which is nasty, really hard, really horrible equation set, to a much simpler one. Now, you may think, well, hang on, if that assumption is not valid, how can we still use it? Okay, so we're going to have a look at a bit of the physics of water at the moment. Right, here we've got a diagram. Okay, this is sort of, let's say this is the bottom, what we call the datum, or the face of, it could be the bottom of a swimming pool or something like that. Okay, and this line here is just a wave in the water, so it's like undulation in the water. Now imagine that wave is traveling from left to right. This dashed line here is what we call the mean or still water level. So if you would take the water in your tank or whatever water you have, average it all, you have this dashed line. So if you had a swimming pool, left it for a while, all the waves sort of settle down, it'll be all still. You're still at that dashed line. So the distance between the base and the dashed line are called D, the depth. Lambda is what we call the wavelength. Now, the wavelength is the distance between two corresponding points on the wave. So, for example, if this is one wave, okay, if I go from trough to trough, okay, so there to there, that gives me a distance, and that's our wavelength lambda. This is considered deep water when the distance divided by the wavelength is greater than 1/2. And in deep water, the motion of a particle in the water follows this circular motion. So if I had a mutually buoyant particle, that means it's not going to float or sink, it's just going to be in the water. Okay, and if my wave is going from left to right, what will happen is you'll have a circular motion there. Okay. So we can measure this. What we do is we stick in some little particles, some luminous particles in water, and we film it. And then we can use motion tracking to track the motion of particles, and it follows a circular motion. As we go deeper, the radius of your circles gets smaller and smaller. Until about only 1 meter or 2 beneath the surface, you don't feel it. Anybody here ever done scuba diving? Scuba diving, snorkeling, diving, anything like that? Nope. Okay. Got to do it. It's great. It's great. If you ever go diving, once you get more than a couple of meters under the surface, you don't feel the waves. The waves are on top of you. And this is what this is showing. Okay, so just because the surface waves, it can be really, really rough sea. As soon as you go a couple of meters down, you don't necessarily feel the motion of the waves. You may feel turbulence, which is maybe affected by the waves or vice versa, but you don't actually feel the motion of those waves. The reason being is because the radius of this circle here gets smaller and smaller. So that's what happens in deep water. As the depth decreases, the behavior of the wave changes slightly. So here I've got the same wave, but imagine this D is less than that. I know it's the same, basically the same diagram, but imagine this D is a lot less. Okay, the wavelength is again lambda, depth, and we call intermediate depth water, the depth wavelength is somewhere between 1/20th and 1/2. And what motion of particles tends to be in an ellipsoid. Okay, so we have an ellipse, and the minor axis, which is the smaller part, gets smaller, the smaller radius there. Okay, so we have a major radius, which is that distance, we have a minor radius, which is a smaller one. Okay, that gets smaller and smaller. Okay, it's just the property, the physics of water. If D is quite small, and we have depth to wavelength ratio of less than 1/20th, we have what we refer to as shallow water. And again, if we track the motion of particles, what they tend to do is go in a horizontal direction. They don't tend to sort of rotate like that, they just tend to go back and forth. And this is why the shallow water equations are applicable, but only when the depth to wavelength ratio is less than 1/20th. If you wanted to model water where the depth to wavelength ratio is greater than 1/20th or even greater than 1/2, you couldn't use shallow water equations. But it's a simplified model, and that's what we're going to be looking at today. Okay, here it is. This is what we call the 1D shallow water equations. Just one spatial dimension, so we're not bothered with the y direction, we're just bothered with the x direction and height. Okay, have a look at this diagram first. Okay, so there's our x direction. Okay, the vertical axis I've labelled z, straight up. If we had the 2D shallow water equations, we'd have another horizontal axis being y. What we have here is we have like a beach. Think of this as being the beach, so this grey area, and that's your bed surface. Okay, so above that beach is our water, below it is sand, rock, soil, that sort of thing. Okay, and the height of your bed surface is denoted by ZB, or Z normally. The dependent variables in the PDE are h which is the water height, okay, and u, which is the horizontal velocity. Okay. Now, if I was to move this arrow up and down, the water height would change. Okay, so depending on where you are in the domain, you have a different value for h, and you'll also have a different value for u. Okay, so u is just horizontal velocity. When u is positive, your water's flowing left to right. When it's negative, it's flowing right to left. Water acts under gravity, so we've got a gravitational force pushing the water down. Okay, so that's 9.81. That should be a -2 there. Did it say that in the notes? Was it -1 or -2? Yeah, that's right. It's correct in the notes. Okay, so h and u are your independent variables. Okay, and we have two equations in our system. So the first equation is derivative of h with respect to t plus h times u with respect to x equals 0. By the way, h is height, which is also mass. U is velocity, so mass times velocity is momentum. So h times u is momentum. So that means the change in mass over time plus the change in momentum over space is equal to 0. So that's conservation of momentum. Sorry, conservation of mass. The next one is conservation of momentum. Okay, so here we have momentum, which is h times u with respect to t, plus this term here, horrible term, sort of known as the flux term. Okay, that's what is the change in momentum over space, and it's calculated as that. I'm not going to ask you to derive that at all, that's kind of given. We've also got gravity times the derivative of z over x. Okay. For a lot of what I'm going to be talking about today, is z, we're going to assume a flat bottom. So ZB used to be 0 everywhere. But if you did have like a beach like this, okay, the derivative of ZB with respect to x is just a gradient of this line. Multiply that by gravity, and that's subtracted to the momentum. Okay, so in this case, this term here is actually having a negative effect on the velocity. So in other words, as a wave moves up the beach, gravity is trying to push it back down the beach. Okay, so those are the shallow water equations. You see there are two equations here, so we have a system of two equations rather than just one. Okay, first equation is conservation of mass, second equation, conservation of momentum. It's for convenience, we tend to write our systems using vector notation. Okay, so you see the bold U means we have a vector of U, bold F is our vector of what we call our flux terms. Flux means how does it change over space. And S is what we call our source terms. S is all about what's happening to the bed surface. Okay, so in this case, U, okay, because we got U with respect to T, in the first equation we've got H with respect to T. In the second equation we've got HU with respect to T. So my U vector is H and HU. Our F is what we're differentiating with respect to X. So we've got HU for the first equation, and we've got HU squared plus a half GH squared for the second. Source terms is what's happening in this case to the bed. In the first equation we have nothing, so 0. Second equation we have minus G derivative of Z, so therefore we've got minus G derivative of Z. So U is what we call the vector of conserved variables. So that contains H, mass and momentum. So H and H times U. F is called the flux vector. S is called the vector of source terms. Okay, I did mention a couple of slides ago, all the way down here, that when the depth to wavelength ratio is less than 1/20th, that's when we could use the shallow water equations. So that you may be thinking, well, hang on, doesn't that restrict where I can actually use this? Okay, well, one of the most common uses for shallow water equations is modeling tsunamis. You know what tsunami is? Usually seismic activity under the sea floor, what it does, it pushes up plates. So plate tectonics come together, continental plates, one of them will sort of push up over the other, and it just displaces many millions of sort of cubic meters of water. And that disturbance under the sea, so the seismic activity, pushes water around. You will barely notice it. So if you're out at sea in a boat, okay, you're in a boat and seismic activity happens, you may feel a little sort of very gentle, sort of a meter wave. Okay, very gentle. You barely notice it. What happens is, as all that water is moving along the sea, as it gets into the shallower regions, it starts to steepen because of the effect of gravity. Okay, so as it gets, this is a positive. This has got a positive derivative or positive gradient. So times that by minus g, you've got a negative effect. So what's happening here is, as the water comes along, it will steepen. We've all been to the beach, or I hope we've all been to the beach. As you know, when waves come up, they steepen and then they crash over. Now, what happens in tsunamis is they steepen and they can be up to 10 meters tall. So we've got many thousands of tons of water crashing into land, and it's destroyed sort of whole areas. So, do you remember the Boxing Day tsunami of 2004? 280,000 people died because of the force of this water. It's so immense. So one of the applications for shallow water is modelling tsunamis. What you see is the average height of sort of deep water ocean is about 4 kilometres. The wavelength of a tsunami is 213 kilometres. So it's such a long wave, and it's got a height of about a metre. So you barely notice it. We divide depth, which is 4 kilometres, divided by 213, you get less than 1/20. So we can use the shallow water equations to model tsunamis, even though technically speaking it's deep water. When we refer to shallow water, it's that ratio of depth to wavelength. So that's one of the applications. Okay. The shallow water equations, when written like that, do they sort of look familiar? Resemble another type of equation you've been working with? Quite similar to the advection equation. You have something differentiated with respect to t, plus something differentiated with respect to x. So in the scalar advection equation, you'd have velocity times this quantity here. But because we've got a flux, the velocity is in the flux. Okay, so this is quite similar to the scalar advection equation. Okay, what we're going to do is we need to estimate how fast our water is going. Now you'll have lots of values of the velocity. Now to calculate the time step based on stability, we need to know what's the fastest possible speed which our shallow water equations can go up to. Okay, so what we do is we linearize the shallow water equations, and we want to write it in this form. So J is what's known as a Jacobian matrix. Have you ever heard of that? Okay. So what we have is we've got two equations. We've got two values for U, two values for F. Now the Jacobian in this case is a 2 by 2 matrix. The derivative of F1 with respect to U1 on the top, and the derivative of F1 with respect to U2. That forms the top row, and the second row is the derivative of F2. I can say it can easily be shown that, and I was looking at these earlier, and I think, hang on, I've missed out a bit of working out here, so I'll show you on the board. Is it? Yeah. Okay, so that's my U, and that's my F. Okay, I want to be able to find the derivative of F1 and F2 with respect to U1 and U2. First thing I need to do is I need to write this in the form of U1 and U2. Okay, so how we do that, for the first one's easy. Okay, we can see F1 is equal to HU. But HU is also equal to U2. So what I can do is, instead of HU, my F1 is equal to U2. Yeah, does that sort of make sense? Okay, there's HU, which is U2. F1 is equal to HU, therefore F1 should be equal to U2. Okay, the tricky thing is for F2. Okay, I have HU squared plus a half GH squared. I'm going to have to somehow write that in the form of U1 and U2. Well, if I ignore the squared for now on the HU, as I just seen, is U2. So I'm going to write U2, but I need U squared. So I've got to square U2. Okay, so we've got U2 squared. U2 squared is going to be H squared times U squared. I only wanted H times U squared. So I've got another H in there. So what I do is, to get rid of that second H, or that H squared, I'm going to divide by H. Now H is equal to U1, so I'm going to divide by U1. And when we divide, it's the same as power minus 1. Does that make sense? Then I've got plus a half times G times H squared. Well, H is just U1, so U1 squared. I've converted my F1 and F2, so they're in the form of U1 and U2. Okay, so now all I have to do is find the partial derivative. Okay, so the partial derivative of U2 with respect to U1, what's that going to be? What's the derivative of 5 with respect to x? Anyone? 0, yeah. So derivative of U2 with respect to U1 is going to be 0. Okay, let's do U1 with respect to U2. So U1 is U2. What's the derivative of x with respect to x? That's 1. That's going to give you 1. Okay, what about F2? So in this case, F2 was U2 squared, U1 power minus 1, just a half G U1 squared. Okay, so if I'm finding the derivative of this with respect to U1, multiply by the power, subtract from the power, so I have minus U2 squared, U1 to the power minus 2. Okay, so multiply that by minus 1. U2 is just sort of considered just as a scalar. And then we take 1 for the power. Do the same here. 2 times a half is 1. And then subtract 1 for the power. Got U1 to the power 1. And I can convert that back to H and U. Okay, so if I convert that back, so I've got minus U2 squared. So that's going to be H squared, U squared, divided by U1, which is H squared, plus G times H. So that's just GH. GH minus U squared. Or minus U squared plus GH. Does everyone understand how I got back to the H and U? Okay, so U1 is just H, U2 is HU, so HU squared is H squared U squared, divided by H to the power 2. Plus GU1 to the power 1, that's just G times H. Okay, and last one. Derivative of F2 with respect to U2. Okay, so U2 is now what we're differentiating with respect to. So we have 2U2 times U1 power minus 1. And the second term, half G U1 squared. Well, there's no U2 there. So that's just going to go to 0. Let's treat it as a constant. Okay, so we have 2 times HU divided by H, which is just 2U. Okay, so our Jacobian for the shallow water equations is CH minus U squared 3U. This way. Sorry?
Can it cancel out H squared?
The H squared and H squared cancel out. So that's why just left with the minus U there. Oh, I've also switched them around. So I've moved the GH to the front. It should be. Yeah, sorry, was that? Yeah. So I could have written minus U squared plus GH. It doesn't matter. Okay, so that's when I said it could easily be shown that. That's just sort of giving you a bit of a breakdown of how we did that. Okay, so that's where that comes from. Oh, in this case, I've written it as minus U squared plus GH. Okay, so what this process is doing is linearizing a nonlinear equation. So we're approximating our nonlinear shallow water equation by a linearized system. I think if you've done the same, if you do chaos, you do a lot of this, calculating sort of what's happening at critical points and things. Okay, J has 2 eigenvalues. I'm assuming you know how to calculate eigenvalues, which is U plus root GH and U minus root GH. Okay, with systems of PDEs, to determine whether they're hyperbolic or not, we have to look at the eigenvalues of the Jacobian. Okay, if they're real and distinct, okay, we have a system of hyperbolic PDEs. So like the advection equation. We want to write this this equation as 2 PDEs similar to the advection equation. That's what I'm trying to do. What I want to do is take my system of 2 equations and write it as 2 linear advection equations. It's a bit of a sort of approximation. This it's not. I can't just write it as 2 advection equations and solve them because it's a linear system, not a non-linear system. Right. So what I want to do is I want to do what we call diagonalizing. So I want to have a transformation on the Jacobian that diagonalize it so I have a matrix of this form. So D is a diagonal matrix 2 by 2 with the eigenvalues lambda 1 and lambda 2 on the main diagonals. And let's say we have some form of transformation. It doesn't matter what it is, by the way. It's just a transformation. Now this transformation matrix T is 2 by 2. Okay. The first column of T is Q1, which is the eigenvector of J corresponding to the eigenvalue lambda 1. And the second column of T is Q2, which is the eigenvector of J corresponding to the second eigenvalue lambda 2. And what I'm going to do is I'm going to apply this transformation to J. Those of you who did graphics with me last year, remember all the rotation mixtures and all that similar thing. Okay, so J times T, well, T is this matrix with column Q1 and column Q2. Okay, well, that's as simple as that. Okay, so J times a 2 by 1. So J is a 2 by 2. Q1 is a 2 by 1. That'll give me a 2 by 1 matrix when I multiply them together. And it will also be the same to Q2. So J times Q2 will also be a 2 by 1. So I can write this using this. Now this is the definition of an eigenvalue and an eigenvector. Okay, so if Q is an eigenvector of J, by the definition of an eigenvector, that's equal to the eigenvalue times Q. Okay, so instead of J times Q1, I can say lambda 1 times Q1. That's the same thing, it's the same vector. And also lambda 2 times Q2. Okay, well, I can also write that line as this. So this is a 2, remember these are 2 by 1, so this is a 2 by 2, multiplied by this square matrix here. That will give me the same as that. And as you can see, that is the D matrix I was trying to get. Okay. Q1 and Q2 is my T transformation. This diagonal matrix here is my D matrix. Okay. If I remember, this is all equal to JT. So if I invert T and pre-multiply both sides, I get T inverse times J times T gives me a diagonal matrix. Doesn't matter what T is, okay, it's a transformation. What does matter is a transformation like this applied to the Jacobian that will give me that diagonal matrix with the eigenvalues on the main diagonal. Right, so let's apply this. Okay, so D is equal to T inverse times J times T. And instead of U, I'm going to write it in terms of W. The reason being is because U is for the shallow water equations. I'm doing it on a different equation. Okay, so I can write the shallow water equations. Okay, so U is equal to TW, so it's some vector W which has been transformed by the matrix T. Okay, and we have this. So this is the shallow water equations. Okay, well, if we pre-multiply by T inverse, we do the same for all sides of the equation, so we haven't changed the equation. Okay, so T inverse times T, well, that would just be identity matrix. T inverse times J times T would be my D matrix. So therefore, I've just got WT, or W with respect to T, plus D times W with respect to X. So this process is what we call diagonalization, or linearization of a nonlinear differential equation. You might have seen something like this if you've done chaos in nonlinear dynamics. Okay, so if we write that out in full, let's say W is W1 and W2. My D matrix is my diagonal matrix of eigen values, and I've got W1 and W2 with respect to X. Okay, I can split those, I can multiply out those, and that gives me two equations like this. Remember, lambda 1 for the shallow water equations was U plus root GH, and lambda 2 was U minus root GH. These are the same as scalar diffection equations. Remember, UT plus VUX equals 0. So there's your UT, that's your V, that's your UX, and we just got two of them. So the U plus root GH and the U minus root GH are the speeds. One's positive, one's negative. So these are the fastest possible wave speeds which we can get from the shallow water equations, and the slowest. So, and that's the case for any hyperbolic nonlinear system. If you want to know what's the speed limit of how fast something can travel in that system, calculate the eigenvalues, and that's your fastest and slowest. So, for example, acoustic problems, okay, that require sort of gas dynamics. What you do is you calculate these, and that happens to be the speed of sound, because your sound can't possibly travel faster than that limit. Why did we do all that? And I can see you're a little bit sort of bunny in the headlights over that. Okay. The reason we did it is because to calculate the maximum allowable time step for our numerical methods, we need velocity. Okay. Okay. In our linearized shallow water equations, the velocities were u plus or minus root gh. Okay. Now, with the advection equation, we had a single value for velocity. So all nodes in our domain had the same velocity. With the shallow water equations, each node is going to have a different velocity. Now, what we've got to make sure is that our scheme is stable for all nodes. So we have to take the worst possible scenario. And the worst possible scenario is the largest absolute velocity, whether it's positive or negative. Okay, so we've got to take the worst possible, or what's the node with the fastest speed? And what we do is we take the absolute value of u plus root gh. And that's the fastest possible speed we have at that time. So for the shallow water equations, to calculate the maximum allowable time step, we have your current number, which is normally 0.9 or something like that, times your spatial step, delta x, divided by your fastest speed. Okay. That's why I had to go through all of that eigenvalues nonsense just now. It's not nonsense, it's quite nice maths, but it can be quite complicated. Okay. So that's a lot of theory. Now let's talk about the actual solution. Now we've been using this scheme in the lab sheet 4 and for the scalar advection equation. That's a Latz-Friedrich scheme for that advection equation. Okay? And that's first order in time, first order in space. Now if we apply this to the shallow water equation, the first thing you notice is your u vectors are now bold. I think in the notes, I might have put these as uppercase just to make it clearer. Okay, so these are now vectors. They're not just single values, they're now vectors. And also, with the advection equation, we have the velocity, which was the same for all nodes, so we just the delta t over 2 delta x. But the flux in the shallow water equation includes the velocity. So we no longer have that v there. It's now actually included within the flux. So this is a scheme. So here you can see our next solution of our vector u is equal to the average of the left and right u vectors plus dt over 2 dx, and then this is involving the flux. Okay, so this value depends upon the u values and also the f values. Okay, boundary conditions. We can use transient flow, or we can use what we call solid wall. Transient flow means water will just flow out of the boundary without knowing the boundary is there. As far as sort of that water is concerned, there's an infinite sort of long channel of water. Okay. So zero gradient boundary conditions, you just set the height of the ghost node to be equal to the height of the second node in the domain, and the velocity of the ghost node is the same as that of the same node, of the second node in the domain. And you use the upper end. If you want to simulate a solid wall, so any water sort of meeting the boundary will be reflected back off of it, the height is the same as the transient flow. So there's a height, same as transient flow, but the velocity is negated. So you can see the velocity of the ghost node is equal to negative for the velocity of the second computational node in the domain. And that will simulate a reflective wall. Okay, to test a shallow water solution, we're going to do what we call a one-dimensional dam break test. Okay, here's our domain. It's 1D, so we're only looking at the X domain. And what we have is we have two bodies of water. This is known as the upstream body. Okay, this is known as the downstream body. And our bodies of water are separated by a partition or a dam. Imagine there's something there preventing that body of water from mixing with that body of water. And this is called the one-dimensional dam break test. It's unusual because it does have an exact solution. I know I keep saying this doesn't have an exact solution, but this one does. So we use it to test our schemes. Okay. And that's what's going to happen to the solution. What happens is when we remove that dam, we instantaneously sort of magically get rid of the dam. What will happen is all the water upstream will just flow under gravity downstream. And it forms what we call a bore wave. So a bore wave is like a sort of vertical sort of wall of water. Okay. But remember, we've got conservation of mass. We can't add any more water to our system. So this water, which has gone down here, has to come from somewhere. So it gets taken from here. So what we have is we have two waves. We have a bore wave, which travels from left to right. We also have what we call a rarefaction wave, which is also a depression wave, which will travel from left to right because of that mass has disappeared off downstream. So that's what we would refer to as the one-dimensional dam break test. Okay, actually, what I'm going to try and do, it was having a bit of hissy fit earlier, but I'll try it again. See if I can get the so it's always better to show you on show it working. Oh no. Oh, there you go. That wasn't very smooth, but that was it sort of working. Actually, I'll go back to the slide. Okay, and you can see the red line is the exact solution. Points are my computer solution. And what you'll notice is the red line has an abrupt change in gradient here. Okay, so that was that discontinuity which you've been looking at in lab sheet 4. And you can see, because it's first order, Lax Friedrichs, we have a smoothing out of that corner. And likewise, we've got a corner here, we have a smoothing out of that corner, and likewise up here. So this Lax Friedrich scheme is not ideal. It does a solution. What I might as well do is actually just talk you through the code for this. Just going to increase the font size a bit, just so you can see. Okay, this code should resemble fairly, should be quite similar to the advection code. Preamble, number of nodes, etc. Time step, sorry, not time step, spatial step dx. Gravity 9.81, and I'd use a CFL or C value of 0.9. So all of that is fairly similar to the advection. Okay, define the initial conditions. So for the height, in this case, I set it to be 1s everywhere. So I've got an array of 1s, but where my x value is greater than 0.5, I set it to 0.5. So to the left of the dam, I've got a height of 1. To the right of the dam, I've got a height of 0.5. Okay, and then we march through the time marching loop. Unlike the advection equation, we're going to have to calculate the maximum allowable time step at each step, because the velocity will change. The maximum velocity, or whatever node it is, will be different. So at the beginning of your time step, you calculate what the maximum value of your time step is. So here we have dx divided by absolute value of u plus square root gh. And what I've done here is dt is equal to minimum of dt, or t max minus t. That just makes sure that t never goes bigger than t max. Just so I stop where I want to stop. So it might go over that. Okay, what have I done here? Calculate boundary conditions. Okay, you can see here I've used reflective boundary conditions. So the height is the same, but the velocity is negated. And here I've calculated my u and f vectors. So u and f are 2 by 1. So the top value is h, and the second value is h times u. Notice it's dot times, because I want each individual element multiplied. Okay, f, same thing, h times u on the top, and then you've got the flux on the bottom. And then you just use a Lax Friedrich scheme, very, very similar to the advection. Once you've got the advection once you've calculated that, we can remove H and U from our, what I've called UNP1, so that's our updated solution. So H is just the first row of U divided by the first row. Remember, it's HU on the second row. Divide that by H, you get U. Okay. What I'm going to do now is just set Tmax to be a bit higher, and then let it run, and you'll see the hopefully you'll see the water bashing off of the sides. Why isn't that not? Something's gone wrong. Like I say, I've had a bit of a hissy fit with this. No, not liking anything. Oh, dear me. Okay, well that occurred. Now I'll give it one more time, one more chance. Oh yeah. I'll try again. Usually runs quicker than that on a computer. As it gets to the end, you'll see it bounces off the side. Okay. Ignore this sort of zigzaggy nature. That's just because it's his attribute scheme. So as this wave gets to the end, it will reflect off that side. Okay, and if I let that go forever, it will eventually just get down, and then it should be averaged at around 0.75. If I just let it keep going. Okay, and it bounces off that end. Right. So that's the solution. Very, very similar solution technique to the advection equation, just a couple of things you have to take care of. And that was this is the solution for H. Okay, that's water. That's the one we most sort of look at when we take a solution. We've also got the solution for the second variable, which is velocity. Okay, again, the red line is the analytical solution, the blue line is the computer solution. Okay, Latz-Friedrichs' first order, that's why it was a bit rubbish. I'm going to actually use a second order scheme now. And this is called the McCormack scheme. Now, this is identical to Latz-Wendroff, which we looked at in chapter 4. But this is a two-step version because the one-step version doesn't work. Okay, so think of it like a predictor corrector. So we have we calculate over the half time step. So we calculate this. And then we update using our half time step values over the full time step. It's pretty much, for all intents and purposes, the same as a Latz-Wendroff, but we can't apply Latz-Wendroff to a system. And here we have the solution using Latz-Wendroff. Straight away you can see it's slightly better. It's resolved that sort of discontinuity a bit better there. But we've got a little bubble, got a little bit of an overshoot there. We've also got a little bit of an oscillation here. So it's not perfect, but it's a lot closer to the red line than the Latz-Friedrichs. And that's the velocity as well. Okay, I'm going to do the 2D shallow water equation next week. Right, what I was going to do is just have a look at a hand calculation example.